Okay, so this chapter is all about heat and temperature, which are actually two different things. We're going to find out. So there's a relationship between heat and temperature and the motion and the position of molecules. Well, that's kind of the main idea of the chapter. Let's see. Yeah, this is just an overview. Some of this stuff we're not going to get into, as you'll see. Probably the most important thing on here is really not for this chapter. This is more for when we get to chapter 9. But a molecule is the smallest unit retaining, and I like to say the chemical properties of a compound. We'll get into that later, though. Alright, and I'm going to skip this solids, liquids, and gases just because there's no homework questions on it. So temperature, so here's the definition of temperature. This is one of your homework questions. Is a measure of the average kinetic energy of the molecules that make up a substance, as it says here. And basically, as the kinetic energy increases, that is, the speed of the molecules increases, the temperature goes up. And that's basically the definition of temperature. So temperature has to do with the motion of the molecules, whether it's a gas or a solid or a liquid. This is true. Okay, so now there's something that happens to most things, not everything, but usually when something is heated, it expands, and when it's cooled down, it contracts. But they do so at different rates. For example, this is what's called a bimetallic strip. It has two pieces of metal, and obviously the brass is expanding quicker than the iron, and so it bends. We actually use that in certain things like thermometers and thermostats and things like that. All right, so there are three major scales: the Fahrenheit scale, the one that we commonly use in the United States, the Celsius scale, which is used by most of the rest of the world, and of course the Kelvin scale, which is used primarily by scientists and engineers. This is the absolute scale where there is the lowest temperature is 0, for example. On the as it says here on the Fahrenheit scale, the lowest temperature is negative 459, and then on the Celsius scale, it's negative 273 degrees Celsius. All right, so we have to be able to convert between one of these, one form and another, and here are the conversion equations. So they're pretty simple. If you have a temperature in Celsius, to convert it to Fahrenheit, you multiply the temperature by 9/5, and then you add 32. If you happen to have the temperature in Fahrenheit already, you subtract, and notice the parentheses here. You have to do what's in parentheses first. So you subtract 32 and then multiply by 5/9. And the conversion to Kelvin from Celsius is you just add 273 to it. So, all right. So that is. I'll do some examples of this a little bit later. All right. Heat. So let's get into the definition of heat. So let's see. Is this? Let's not actually here. Let's find the there it is. So here's the definition of heat. Heat is a measure of the internal energy. Well, first of all, if heat is a form of energy, we should state that right now. And it's different than temperature, right? We know that temperature is the average the average kinetic energy of the molecules that make up the substance. So that's what temperature is. Heat is a measure of the internal energy that has been absorbed or transferred from one object to another, as it says. And you can cool things down, you can heat them up. By heating something up, you're increasing the internal energy. Cooling something down, you're decreasing the internal energy. And when there's a difference in temperature, energy. This is really important. This idea, which turns out to be one of the laws of thermodynamics, is that is when there's a difference in temperature, energy will always flow in from the higher temperature to the lower temperature. That's just the way nature works. And a good analogy of this would be, for example, if you had a ramp and you put a ball on top of the ramp and you let the ball go, the ball always rolls downhill. And it's the same kind of thing, like where heat would flow from higher temperature to lower temperature. There's also a method of heating that doesn't involve a difference in temperature, and that's just a direct energy form conversion. For example, if you're doing work on an object, I'll use a quick example that I always use. If you take a drill bit and you drill a metal drill bit into a piece of metal, for example, it's very noticeable when you do this with a piece of metal. When you do so, the metal heats up. The drill bit heats up as well as the metal that you're drilling into, and that's because you're turning friction. You're doing work by spinning the drill bit, and that turns into friction, and that friction will heat up. And so there's no temperature difference there. You're just converting friction into heat. All right. There are several units of heat. The unit that we use in this textbook and in chemistry as well is a unit called the calorie, and that is the amount of heat, the amount of energy, in other words, to raise the temperature of 1 gram of water 1 degree Celsius. And similarly, there's what's called a kilocalorie, and so that's 1,000 calories, and usually we represent that with a capital C, and that's the energy needed to raise 1 kilogram of water 1 degree Celsius. And let me say something really quickly about this kilocalorie, why this is included. This is actually what we find on food, printed on food. Everything, like when they talk about a candy bar is 150 calories or something like that, or a soda is 95 calories. They're talking about these calories. All right, we're going to be in this unit. We're just going to be talking about these kind of calories for the most part. The amount of energy needed to raise 1 gram of water 1 degree Celsius. And then there's a English unit called the BTU. You still find these, for example, if you buy a heater or something like that they'll give you how many BTUs the heater will be able to put out and so forth. So it's the amount of heat energy needed to raise 1 pound of water 1 degree Fahrenheit. And this is really important, this idea of the mechanical equivalent of heat. 1 calorie is 4.184 joules. So if I want to turn calories, which are units of heat, into units of energy, in general, the general idea of energy, it's 1 calorie is, as I said, 4.184 joules. We'll need this conversion as we move along. And here we come across what's called specific heat. Let me show you the equation real quick. So heat is represented by the capital Q, and that's in calories. The mass here is going to be in grams. The specific heat has some very odd units. Let me just say them right now, but then I'll talk about it in a little bit. They're in calories divided by grams, and also in the denominator with grams is degrees Celsius. Okay, and then the change in temperature. So this is, of course, anytime you have delta T means the final quantity minus the initial, so it's the final temperature minus the initial temperature. Those temperatures have to be in degrees Celsius. So this equation describes basically this observation is that it takes different amounts of heat to change the temperature of, for example, this, going from 20 degrees Celsius to 100 degrees Celsius, and we have the same mass, right? So there's 10 grams of aluminum, 10 grams of copper, 10 grams of gold. Notice it requires, so that these are basically the same amount of material and the same temperature change, right? A temperature change of 80 degrees Celsius. And the only difference is the type of material. And so the only difference in this in these quantities here, these different metals, and this applies to other things besides metals. Metals are very easy to use here, but it's different things. So this, what we're doing is we're measuring what's called the specific heat. So C is called the specific heat, and its units are calories per gram degree Celsius, where the gram and the degree Celsius are in the denominator. I'll do some examples with this shortly. I just want to try to get through the chapter. There are three ways in which heat can flow: conduction, convection, and radiation. Remember and we've already mentioned this, that heat always goes from higher temperature to cooler temperature. So conduction is usually through solid material. Here, let's take a quick look at that. You heat up one end of a piece of metal, and that heat will flow from molecule to molecule. So that's what's called conduction, usually in a solid. Convection. Let's get to convection. Convection is when heat flows where the heat is the material is physically moving from one location to another. For example, and this convection is generally with what we call fluids, which can be considered gases like the air, for example, in this example, or even liquids, like if you're boiling water, the hot water rises and then it cools off, and so you get these what are called convective currents. So that's convection. And then the last one, radiation, is basically using light, electromagnetic radiation. Light is the visible part of the spectrum anyway, is what we see, obviously. But there's other forms of radiation. There's microwaves. There's also infrared and other X-rays and things like that. This is the only form of heat transfer that can cross a vacuum. The other ones can't, right? Because conduction is hot material going from one molecule to another,